Now let us see the further conditions in this topic. First we started with constant. Now we consider the linear equation. How a linear equation in N converts a given homogeneous reference relation into the non-homogeneous. Say, let us consider the reference relation Fn minus 7 times f of n minus 10 times f of n minus 2 is equal to 8n plus 6 is equal to 8n plus 6. But it says f of 0 is equal to 1 and f of 1 is equal to 2. Solve this recurrence relation. Now it is clear this recurrence relation is non-homogeneous. Why? Due to the presence of this term, it is a linear equation. If it was in the form of this, then again we consider it is a reference relation of non-homogeneous type containing the linear equation. Then we are concerned with only n. Again we start with the homogeneous part. The characteristic equation of homogeneous part is Fn minus 7 times Fn minus 1 plus 10 times Fn minus 2 is equal to 0. The order is 2. R square minus 7R plus 10 is equal to 0. We can factorize it. R square minus 5R minus 2R plus 10 is equal to 0. R minus 5 minus 2, R minus 5 is equal to 0. It means R minus 5, R minus 2 is equal to 0. It means R is equal to 5 and 2. The condition is both roots are different. If both roots are different in the homogeneous part, then what is the general solution? General solution is equal to A1 into first root raised to the power n plus A2 into second root raised to the power n. It is a general solution. Now, what's about the particular solution? Let the particular solution for 1 is, see, it is linear, and in front of the linear we always consider the particular solution as a linear. That is, see that Ps is equal to Q0 plus Q1 n. Q0 and Q1 again are the constants like A1 and A2. No, this time it is clear this particular solution contains n, and this n will change as we change the values of n from 1 to so on. Now, what to do? Put this particular solution in number 1. Always put in given reference relation. Then how it affects the given reference relation? See, here first term is Fn. It contains n. That is, for the first term it is Q0 plus Q1 n. For this constant remains as it is minus 7 into Fn n minus 1. N changes into n minus 1. Similarly here we write Q0 plus Q1 into n minus 1. Here we changed n to n minus 1. Now for this term n changes to n minus 2 plus 10 times Fn minus 2 means Q0 plus Q1 into n minus 2 is equal to 8n plus 6. It is a substitution of particular solution into the given non-homogeneous reference relation. Now from here we can find out the values of Q0 and Q1 by using the simple concepts of algebra. Here Q0 plus Q1n minus 7 times, it is Q0 plus Q1n minus Q1 plus 10 times Q0 plus Q1n minus 2 times of Q1 is equal to 8n plus 6. What we do? Compare the coefficients. Compare the coefficients of like powers on both sides. We see here is only one power n contains 1. Say we compare for n. Here find the terms which contains n. It is Q1 minus 7 times Q1 plus 10 times Q1 is equal to 8. This side the coefficient of n is 8. So simplify it, that is 4Q1 is equal to 8. This implies Q1 is equal to 2. We have find the value of Q1. Now second option is we compare the coefficients of constant terms, which does not contain n. Let's see. For the constant terms, here we count first constant term Q0, then minus 7 Q0 plus 7 Q1 plus 10 Q0 minus 20 Q1 is equal to 6. Here on the right hand side, constant term is 6. Calculated 10, 11, that is 4 Q0 minus 13 Q1 is equal to 6. Q1 is equal to 2. 4 Q0 minus 13 into 2 is equal to 6. 4 Q0 is equal to 32. Then Q0 is equal to 8. Therefore, particular solution is equal to Q0. It means 8 plus, what is Q1? 2. 8 plus 2. It means what we see, if the non-homogeneous terms is in the linear form, again the particular solution is in the linear form. Now we can collect all the informations for the final solution. Let's say the final solution Fn is equal to general solution plus particular solution. Fn A1 into 3 raised to the power n plus A2 into minus 2 raised to the power n. It was the general solution. What is the particular solution? Plus 8 plus 2n. Take it number 3. No. If these conditions are not given, then it is the final solution. If these are given, again we see how to calculate certain relations. Then from the first condition, f of 0 is equal to 1. This implies 1 is equal to a1 3 raised to the power 2 plus a2 minus 2 raised to the power 0 plus 8 plus 2 into 0. Here n is 0. And 1 is equal to a1 plus a2 plus 8. Or we say a1 plus a2 is equal to minus 7. Say it is equation number 4. Similarly, we can use the second condition, that is f of 1 is equal to 2. It means 2 is equal to a1 into 3 raised to the power 1 plus a2 into minus 2 raised to the power 1 plus 8 plus 2 into 1. That is 2 is equal to 3a1 minus 2a2 plus 10. 3a1 minus 2a2 is equal to minus 8. Say it is number 5. Now we can solve both equations simultaneously. So multiply it by 2, we get 4 into 2 plus 5. That is 2a1 plus 2a2 is equal to minus 14. 3a1 minus 2a2 is equal to minus 8. It cancels, that is 5a1 is equal to minus 22. From here we get the value of a1, that is equal to minus 22 upon 5. So put it anywhere in 5 or 6 or 4. From put in 4. And we get a1 plus a2. a1 means minus 22 upon 5 plus a2 is equal to minus 7, or a2 is equal to minus 7 plus 22 upon 5. That is equal to minus 35 plus 22 divided by 5. That is equal to minus 13 upon 5. Again we have calculated the constants a1 and a2. If we put these values here, we will find the final solution. That is Fn is equal to a1, it is minus 22 divided by 5 into 3 raised to the power n plus a2, it is minus 13 upon 5 into minus 2 raised to the power n plus 8 plus 2n. It is the final solution for a non-homogeneous exponential relation which contains the linear term which depends upon n. No. Remember one thing, only sometimes we can represent only the particular solution. Then no need to find out these homogeneous solutions. Only start with the let the particular solution is equal to this and end it at this point. Let's proceed this theorem. First we discussed about constant, then linear. Now we discuss about a quadratic term in a non-homogeneous linear part. Here we will do only find, say, particular solution, only particular solution for Fn plus 5 times Fn minus 1 plus 6 times Fn minus 2 is equal to 3n square minus 2n plus 1. Again we see on the right hand side it is a homogeneous part, but left hand side it is the homogeneous part, and on the right hand side it is a quadratic. Remember, it is also quadratic, it is also quadratic, but it is given it is a perfect quadratic. Okay? We are concerned only with the power of n. If it contains only these single terms, again we consider it is a quadratic term. Now only we have to find the particular solution. On the right hand side it is the homogeneous part, we can solve it as we discussed in the previous part. Now we see only the treatment for this term which converts the homogeneous part into the non-homogeneous part. Let particular solution of 1, we consider it number 1. Here quadratic, and in front of quadratic the particular solution will be again the quadratic. The particular solution we consider, say, Q0 plus Q1n plus Q2n square. It is again quadratic. See, it is also quadratic. Its particular solution is again this. Its particular solution is again this. its particular solution is again this. But for this, the particular solution is the previous example we discussed. What we do? Put the particular solution in 1. Put in 1. Remember, we have two terms n and n square. When we put in these terms, then they will also change according to this term. For Fn, we write it is Q0 plus Q1n plus Q2 n square plus 5 times. Here it is Fn minus 1. It means here every n will change into n minus 1. 5 times Q0 plus Q1 n minus 1 plus Q2 n minus 1 whole square. For the third term, constant remains as it is. Term is Fn minus 2. Fn minus 2 means change the n into n minus 2. That is Q0 plus Q1 n minus 2 plus Q2 n minus 2 whole square. That is equal to right hand side 3n square minus 2n plus 1. What we have done? We have selected the particular solution which is again a quadratic form for this term containing n which is in the quadratic form, and we replace the each term of the recurrence relation by this particular solution. Terms containing n, here n remains n. Terms containing n minus 1, n changes to n minus 1, and the terms containing n minus 2, the term changes to n minus 2. No, here the algebra, basic algebra is applicable. Let us say Q0 plus Q1n plus Q2 n square plus 5 times Q square plus Q1n minus Q1 plus Q2 n square plus 1 minus 2n plus 6 times Q0 plus Q1n minus 2Q1 plus Q2 into n square plus 4 minus 4n is equal to 3n square minus 2n plus 1. As much as we simplify this equation, we will be comfortable in the further calculations. We can compare coefficients of like powers, on both sides. Here we have three types of the terms containing n square, n and the constant. Now we start with n square. That means we are comparing the terms containing n square. See, from the left side it is Q2, then plus 5, and this term is Q2 n square. It means plus 5 Q2, and from here 6, and this term is Q2 plus 6 times of Q2 is equal to, on the right hand side, coefficient of n square is 3. That is 12 Q2 is equal to 3. This implies Q2 is equal to 3 by 12, that is equal to 1 by 4. Now we try it for constant for term n. For n, see, in the first bracket the coefficient is Q1, for the second bracket 5 Q1, then this minus 2 Q2 and 5 minus 10 Q2 plus 6 Q1, this Q1 containing n, then Q2 with this term It means minus 4 Q2 into 6, it is minus 24 Q2 is equal to, on the right hand side, n is coefficient of n is minus 2. 12 Q1 minus 34 Q2 is equal to minus 2. Q1 minus 34 into what is Q2? 1 by 4 is equal to minus 2. That is 12 Q1 is equal to minus 2 plus 17 by 2. That is equal to minus 4 plus 17 by 2. That's equal to 13 by 2. It is Q1. Now only one coefficient is left, say constant term. For the constant terms, we compare here. For the constant terms, on the left hand side, constant terms, we start from this bracket. It is Q0, it is 5 Q0 minus 5 Q1, then plus 5 Q2 from here, plus 6 Q0, 6 Q0 minus 12 Q1 plus 4 Q2 into 6 plus 24 Q2 is equal to, on the right hand side, constant term is 1. It is 12 Q0 minus 17 Q1 plus 29 Q2 is equal to 1. Here 12 Q0 minus 17 Q1 means 13 by 2 plus 29 into Q2. Q2 is 1 by 4 is equal to 1. It is 12 Q0 minus, let's multiply it, 221 divided by 2 plus 29 divided by 4 is equal to 1. 12 Q0 is equal to 1 plus 221 by 2 plus 94 divided by 2. 4 plus 442 plus 92. That is equal to 12 Q0. That is equal to 475 divided by 4, and Q0 is equal to 474 divided by 12 into 4, that is equal to 475 divided by 48. Now we have calculated all the three constants. Then what is the particular solution? Particular solution was Q0 plus Q1n plus Q2 n square. Put the values of Q0, Q1. Q0 is 475 divided by 48 plus Q1 13 by 2 n plus Q2, it is 1 by 4 n square. So it is a particular solution. Rather, algebra is application of algebra is rather hard, but the procedure is a fixed. So single theorem we can extend constant to constant, linear to linear, and quadratic to quadratic. Now in this case we see some particular case